So on Tuesday we were talking about logarithms, and we finished up having some laws of logarithms, and so today we're actually going to practice using those laws to manipulate all sorts of equations and expressions involving logarithms. So that's our task for today. So let's go back and remind ourselves what a logarithm is. So here was the definition that we had from Tuesday. It said, the logarithm of a number to a given base, where that base is a positive number, not 1, is the number that the base must be raised to give that number. So in other words, if I had the log of 16 to the base 4, that says, what power must 4 be raised to give 16? And the answer is 2. So the log of 16 base 4 equals 2 is the same statement. These are the same thing as saying 4 squared is equal to 16. Those two things are exactly the same statement, just expressed in different order. And I did finish off towards the end on Tuesday saying the natural logarithm is the logarithm where the base that we use instead of being 4 is the number e, is Euler's number, which is an irrational number about 2.7. And it's irrational. And so if I were to say ln, that's our shorthand for natural logarithm. So ln 16.5 is the same as saying log to the base e of 16.5. And I can't do that in my head, but if you have a look on your calculator, there should be an ln button on it. Have a look to see if your calculator actually has an ln button on it. And go ln 16.5, and hopefully you get something like 2.803. So that is saying, here that would be equivalent of saying e raised to the power 2.803 would be a number that is approximately 16. Again, your calculator will have an e to the x button, if you have a look. And if you were to work out e to the 2.803, you'd get a number that's close to 16. It wouldn't be exact because I didn't retain all the decimal places here in the first answer. But it should be very close to 16, I would say. The other button that your calculator on it has, it's a log button, and it assumes that the log base is 10, and that's called a common logarithm. So your calculator has a log 10 and a log e buttons on it. And as we shall see in a couple of minutes, that's all you'll ever need. We don't need logs to any other bases. Okay, so let's now have an example of trying to solve an equation that has logarithms in it. Now, there's a couple of things to remember in here. The first is log 3.5. It's a number. It's the power that e must be raised to give 3.5. But it is just a number. So therefore I can subtract by log 3.5. I can divide by log 3.5. I can multiply, so forth. So I can do arithmetic with that thing, treating it as a number. But we also have some log laws that tell me some special properties about these numbers. So I'm going to be doing two things as I manipulate this equation. I'm going to be using normal algebraic operations, which are just based on arithmetic. And I'm also going to be able to use the log laws that we had last week to help me manipulate this. So let me start. I'll do this a couple of ways. But to solve an equation for x means, if I can, I want to make x the subject. So that's my task. So I'm going to get all the terms not involving x on one side and all the terms involving x on the other. So I'll do that. Here I'll say, therefore, 2 log x is equal to minus 2 minus log 3.5. So these terms don't involve x, so they're on the right-hand side. Left-hand side has the terms involving x. I can then divide both sides by 2, and I will have log x is, now this would be minus 1 minus a half log 3.5. Now this says the log to the base e of x is this number here. So that tells me that e raised to that number must give me x. That's the definition of our logarithm. So I can say, therefore, x is equal to e raised to the power minus 1 minus a half log 3.5. And there is my value for x. If you were to evaluate that on your calculator, somewhere along the line, I've got it here, I think you get a number like 1.966 to 4 decimal places. Something like that. Now, sitting here, so that seemed fairly straightforward, I would hope, if you can remember your algebra skills. But in here, this is not the only way in which I could have manipulated this. There's, well, let's just say a lot of different ways. Let me show you some other ways in which I can get this same answer. So what I might do, so same equation, just a different approach. No one approach is better than the other, they are just different. So here I can go. So I have log of 3.5 plus 2 log x is equal to minus 2. Now this time I'm going to use some of the properties that I know about logarithms. So one of them is this, so I can say that's the same therefore as log 3.5 plus log x squared is equal to minus 2. And sitting in there I used the log law that n log, it doesn't matter what base you use, is log x to the n. That was one of the log laws we had last week. So I've used that. I can now combine these into a single logarithm. I'll say this is log 3.5 times x squared is equal to minus 2. And sitting here I have used the fact that log x plus log y is the same as the log of x times y. That's the log law I've used there. Now, I get to the stage here, the log of this is minus 2. So this is log to the base e. So therefore, 3.5 times x squared has to be e to the minus 2. We'll try harder. Awesome.
Sorry, I don't know what that is.
It's okay. We enjoyed it. Okay. So now let's divide both sides by 3.5. So I have x squared is, now I guess I'll write it like this. E to the minus 2 on 3.5. And that's the same as using my laws of indices, 1 on e squared times 3.5. Doesn't matter which way you write that. Now, if that's x squared, to find x becomes the square root of 1 on e squared times 3.5. And I took the positive square root here because sitting in our original equation here, I had log of x. And we know that the domain of the log function is just the positive values of x. And so therefore I don't want the negative square root because I can't put it back in the original equation. So we have to say take the positive square root, take the positive square root because the domain of log, doesn't matter what base, x, is the set of all x such that x is greater than 0. So that's what we've done there. Now, I can simplify this a little bit because going back to our algebra days, we remember the square root of a over b is the square root of a over the square root of b. Now the square root of 1 is just 1, so this becomes 1 over. Now I've got the square root of e squared times 3.5. I can make that the square root of e squared times the square root of 3.5, and the square root of e squared is just e, and so I end up with just that. 1 on e to the square root of 3.5. Those two numbers are the same numbers. I've just done some arithmetic sitting in there because I know my laws of arithmetic and I've used them there. You could quite happily get your calculator out and work that out and get, hopefully, what we've got over there, 0.1966. Now, that answer as it sits looks a little bit different to this answer over here, but we know some laws of indices sitting in here. For example, I know that e to the a plus b is e to the a times e to the b. For example, that's one of our laws of indices. So I can actually write this here as e to the minus 1 times e to the minus a half log 3.5. That's using one of just straight laws of indices sitting there. E to the minus 1 I can interpret via my laws of indices as being 1 on e. This one here I can't do much with unless I invoke one of my log laws, which is here e to the log 3.5 to the minus a half. I've used this log law again, where n's minus a half. Minus a half log x is log x to the minus a half. So I've used that. Now, this log here, it's log to the base e. It says, what power must e be raised to give 3.5 to the minus a half? I don't know what that power is, but if I raise e to that power, I must get 3.5 to the minus a half. So this becomes 1 on e times 3.5 to the minus a half. The minus a half we know is 1 on e times 1 on 3.5 to the half, which is 1 on e times 1 on the square root of 3.5. And now my two answers look very similar. In fact, they look exactly the same. So sitting in here, I would quite happily accept this as an answer to the equation, but there's lots of other different forms in which that answer could have been written. They're all equivalent, and being able to get all of the equivalent laws, or equivalent, I'd say, ways of expressing this number you need to be able to do your algebra. You need to know your laws of indices, and you need to know your logarithmic laws. And also you need to have some practice in working with them. Unfortunately, there's no substitute for practice. The more practice you do, the better you'll get at it, I would say. I imagine these days most of us would actually just go for the calculator from there. And that'll probably be all right in most occasions, I would say. Although I can envisage myself asking an exam question saying, which of these expressions is equivalent to that? That would make a good exam question. I just thought that up. I'm going to put that in the exam. Okay, you got it? I haven't set the exam yet, so I'm right. I guess, sitting here, we could conceivably check whether that answer is correct by going back up here and putting it in. But I think checking the answer is probably harder than finding the answer. So I'm not going to check it, I'm just going to trust I got it right. But we could conceivably check the answer, sitting in there. So I will leave that there with you to think about. The next question says this. Find it... Okay, I guess the other thing is, sitting here, I found an exact value for x there. I found an approximate value for x there. So in this case, it was quite possible to find an exact value. In this question, it asked just for the approximate value. And in fact, I don't think you could do any better. If you were asked for the exact value, that is the exact value there. That's as good as we could do. So this one's asking for an approximate value, and so therefore resorting to our calculator is a good thing. The only problem is our calculator doesn't have a log 2 button on it. It's got a log base 10, log base e. So, actually, I take that back. There are some calculators that do have other log buttons on them, but I don't think you're likely to have one. I could be wrong. Someone might have a fancy calculator and prove me wrong, but it doesn't matter. I'll show you what to do. So sitting here, so I want to find an approximation. I'm going to let that approximation be x. I don't know what it is, but my job is to find it. 1.34. So this says, what power must 2 be raised to give 1.34? So another way of writing this is to say, therefore, 2 to the x is the same as 1.34. Those two statements are equivalent. And I guess that's the moral of this whole section, isn't it? Those two statements are equivalent. If you can get your head around that, you should be able to get your head around most of what we do here. Okay, so here we go. Now what I'm going to do is I'm going to take a log of both sides. If 2 to the x is equal to 1.34, then the log of 2 to the x must be equal to the log of 1.34. But the base I'm going to use now is a base that I've got on my calculator. So I'll use base 10. So I'll say, therefore, log base 10 of 2 to the x is log base 10, 1.34. I'm going to make use of this log law yet again. This time I've got log base 10 2 to the x, so that's going to be x lots of log of 2 to the base 10. So using my log law again, this will be x log 10 of 2. And on the right-hand side, I won't do anything with that for the minute. 1.34. And now all I have to do is divide both sides by this number here, log 2 to the base 10. So x will be log 10, 1.34, divided by log 10 of 2. And I can do both of those on my calculator, and hence I can get an approximation. And when I did that, here I got something like 0.4222 to 4 decimal places. So that says what power must 2 be raised to give 1.34? And it's saying something like 0.4. The square root of 2, which would be 2 to the half, is about 1.4. So being just a little bit less than a half, that seems actually a reasonable answer. See there? It's just a little bit less than the square root of 2. Interestingly in here, I chose to use log base 10 because that was on our calculator. Our calculator also has a log to the base e button. So I could have just as easily come here and said, look, log base 2 is equal to log of 1.34, where my logs are now to the base e, the natural logarithm. My log laws are still the same. So this would be x log 2 is equal to log 1.34. And so x could be log of 1.34 over the log of 2. And if you do that with the base e, you get exactly the same answer, 0.422. See there? So it doesn't matter which particular base you choose. Same answer. So choose whichever one you like. I quite often use base e in this case because ln's quicker to write than log base 10. That's all. No other reason. And so this will work no matter what logarithm, what base logarithm you've got. You can always put a logarithm in one base in terms of logarithms to the base 10 or logarithms to the base e. So that's why your calculator only has those 2 buttons, because that's all you need, in fact. And so we can say in general, in here, this. So that's how you change from one base to another base with logarithms. If you've got log to the base e, b, then it's log to the base 10 over log b to the base 10. That's all you have to do. So I'll just say in here, this is true in general. So here's another equation that we want to solve for x. So once again, we're going to try and make x the subject of this equation. Previously, when we've had equations like this, what we've had to do, or what has happened, is the numbers have worked out so fortuitously that I could write the right-hand side in terms of 3 to some power. But in this case, the numbers aren't worked out so nicely, and I don't know what 2 is written as 3 to the power something or other. So what we do in this case is we use logarithms. And so here I'm going to take the log of both sides. Take the logarithm of both sides. And if I can just go back here, I'm going to use that log law yet again. Right? These 2 here are turning out to be our most frequently used log laws. They're the important ones. So I'm going to use that one again. So I have log, and you can use any base, but I'll use base 10 because that's what my calculator has. 3 to the 5x minus 1 is equal to log to the base 10 of 2. Using that log law, sitting over there, I can write this as 5x minus 1 log base 10 of 3 is equal to log base 10 of 2. Log 3 base 10 of 3, that's just a number, so I can divide both sides by that number. I'll get 5x minus 1 is equal to log base 10 of 2 over the log base 10 of 3. And now, using my algebraic skills, I'll add 1 to both sides and divide by 5. And so x will be 1/5 of log 2 over log 3 plus 1. And there's my answer for x. And once again, I could conceivably stick it up in here and see if it works, but I'm putting that in the too hard basket. Too hard to do. I think it works. Interestingly, so that's the exact answer. An approximation to this would be, when I worked that out, I got 3262 to 4 decimal places. Once again, I can write this number in lots of other equivalent ways. So let me do some of those. For example here, I could write x as, now in here I could put these over a common denominator, put everything here over log 3. And so then I would have log 2 plus log 3. That's over a common denominator. Now, using the second of the log laws I've got there, the log of 2 plus the log of 3 is the same as the log of 2 times 3. So this becomes the log of 6. So this will become 1/5 log 10 of 6 all over log 3. And so they're all equivalent ways of writing that same number. No one of those is preferable over the others. They're all just equivalent ways of writing the same number. Interestingly, in here, I used log to the base 10. It conceivably would have made some sense if I'd actually, given that I've got 3 raised to something, if I'd actually used logs to the base 3. I could have used log to the base 3 there. So I'll just go here as an aside. I could have said the log to the base 3 of 3 to the 5x minus 1 is equal to log to the base 3 of 2. And using log to the base 3 is a good idea because this says, what power must 3 be raised to give 3 to the 5x plus 1? Because the answer is 5x minus 1 in there. So this says 5x minus 1 is equal to log of 2 to the base 3. So x is log 3 to the base 2 plus 1, 1/5 of all that. I'll put that like that. X is equal to 1/5. That's supposed to be 1/5 there, guys. That's a terrible 5. And so you can see it's fairly quick to solve that if I use log to the base 3. The only trouble is when I come to get an approximation to work out log of 2 to the base 3, I haven't got that on my calculator. So what I would have to use is my change of base formula. And when I do that, Here I get 1/5. Now the log of 2 to the base 3 is the log of 2 over the log of 3. And lo and behold, it's exactly the same answer as I had up there. So it doesn't matter which way you go. Either way is just fine. But as you can see, we are hoping that you will become proficient at manipulating expressions that involve logarithms and indices. Okay? And so we're building up more skills in your algebra repertoire here.